All right, welcome to the online causal inference seminar. Today we have Edward Kennedy from CMU talk about optimal doubly robust estimation of heterogeneous causal effects. He will stop from time to time to take questions from the audience, so please submit questions via Q&A. After that, we have a short discussion by Jamie Robbins, and then if we have time left, we will take some more questions from the audience. All right, thanks for joining. That's it from my side for now. I'm now going to switch over to Guillaume.
Thanks, Dominique. So as Dominique said, the questions to the speaker should be submitted via the Q&A section. We don't have a co-author in the Q&A today, so I will basically be collecting the questions that you have and submitting them to Ed when he stops. So the way it's going to work is I'm going to select some of the questions, and if your question is selected, I will ask you to raise your hand so that I can find you easily, and I will unmute you. Please do not raise your hand unless I ask you to do so. So that's basically how it's going to work, and that's it on my side. So I now turn the mic to Ed whenever you're ready.
Thanks a lot, Guillaume. Thanks everyone for organizing. Yeah, these seminars have been really fun. Share my screen. All right, let's get started. So this is some new work I just submitted to arXiv last night. So it's about doubly robust estimation of heterogeneous causal effects. Just jump right in. Oops. Yeah. Sorry, I'm gonna reshare here. Right, so conditional effects, these are conditional causal effects given sort of subject-specific covariates. These are really crucial across medicine, across the social sciences. So they can be used for a number of purposes. One, just to improve understanding of variation across individuals, but also to inform policy, and they're a crucial part of optimal treatment assignments. So the typical thing that people go after in these problems is I'm calling the conditional average treatment effect. So this is just the expected potential outcome if you're treated versus untreated given covariates X. And so there have been tons of methods that have been proposed recently, especially in the last 5 years for estimating this kind of thing. But there are a lot of interesting theoretical gaps in this work. And this is especially true when this conditional average effect, or CATE, has some non-trivial structure. So some smoothness or sparsity, for example, that's different from what you might see in the rest of the data generating process. So just to give you sort of an overview of the main goals of this work, so that there's sort of two broad goals. The first is just to provide some flexible estimators of this conditional effect, this CATE, that gives stronger guarantees for sort of a wider variety of methods. That's the first goal. It's sort of more practical. It's aimed at giving methods that can be used in practice with nice guarantees. The second goal is more theoretical. So this is all about sort of trying to understand the benchmark for estimating the CATE, the conditional effects. What's the best possible performance that we could hope to achieve in this problem? So those are the main goals. So I'll jump right in. So the setup here is sort of the classic causal triplet that we see in causal inference. So we're going to think about the case where we have in IAD observations of this triplet of covariates X, which are living in RD, treatment A, which is binary here, and an outcome Y. And there are a few characters in this story that play an important role. So one is the propensity score pi. So this is just the chance of being treated given covariates. What I'm calling the outcome regression. So this is the expected outcome given covariates and given a particular treatment level. So I'll call this mu A. And then a third object, which will come in the second half of the talk, is the marginal outcome regression. So it's just the expected value of Y given X. All right, so what's the target here, the statistical target? So under known measured confounding kinds of assumptions, the CATE, the average treatment effect for people with X equals little x, can just be identified as a difference in regression functions under treatment versus control. So mu1 minus mu0. I'm going to call this thing tau. This is a very simple object, right? It's just difference in regression functions at two different treatment levels. You might think we know a lot about nonparametric regression. It's one of the problems in stats that there's a huge literature and lots of solved parts. It turns out by taking a difference, it really changes the problem substantially. We'll see why in just a bit. So here's just a motivating illustration of this this issue of why the difference really changes things. So this is we're going to think about a simple simulated example, a data generating process where we have just one covariate X. It's uniform on -1, 1. Just a simple propensity score that's piecewise constant. And then we're going to think about regression functions mu1 and mu0 that are equal to a particular piecewise polynomial. So if you've seen this Gyorfi book on nonparametric regression, you'll recognize it, and I'll show you it in the next slide. But the important thing is that in this problem, the regression functions by themselves are really hard to estimate. They're non-smooth, they have jumps, and they're not differentiable everywhere, so they're difficult to estimate. But in this case, the two regression functions, mu1 and mu0, are equal. And so the difference is just 0. So it has a lot of structure. It's very simple. In some sense, it can't get more simple than 0. All right, so what would we do here to estimate the CATE? So the easiest thing that you would think of initially is just take an estimate of each of the regression functions and then use the difference. So sometimes I call this a plug-in estimator because we're just taking mu1 minus mu0, sticking hats on them and calling that our estimate. This recent Causal paper called this the T-learner because you're doing two different regressions and then taking a difference. All right, so I just simulated some data from this this process and then used base R smoothing spline to estimate these regression functions, and we'll see what happens. So this is a picture of the data. So the dots are the data points. The plot on the left is the treated subjects, and the plot on the right is the untreated subjects here. And then the gray line is the true regression curve. And remember, this is the same for both the treated and untreated individuals. And so you can see it's going to be hard to estimate. So on sort of the positive X region, it's a little bit easier. It's at least continuous. On the negative X side, there's this big jump, which makes things hard. And so what happens here is, the treated subjects tend to have positive X's. And so on this plot on the left, when we try and estimate this regression curve, we're going to sort of over smooth on the right because this function is sort of easier to estimate. And in the negative X region, right here, we're going to sort of do a poor job of estimating the regression function in that region. So for the for the untreated subjects, the story is the opposite, right? So most of the untreated subjects have negative X's, and this is where the regression function is hard to estimate, or especially hard to estimate. It's sort of hard everywhere, but so that means we're going to pick a tuning parameter that localizes a lot, so we can try and capture this jump that we see. But that means we're going to be way too wiggly on the other side, where there tend to be treated subjects. And so when we take the difference of these two estimates, we're going to get something that's way too complex compared to what it should be, which is just a straight line at 0. And this is a sort of common story. You might expect this to happen in lots of settings. So what should we do about this? So here's a sort of simple fix. So let's imagine for a second that the propensity scores pi are known. Then we could construct this inverse probability weighted outcome, and then just do a regression of this outcome on X. And this thing would behave just like an oracle regression up to constants, as if you actually did a regression using the actual difference in potential outcomes, y1 minus y0. And this just follows trivially because the conditional expectation of this inverse probability weighted outcome is exactly the conditional effect. And so it's going to, this sort of approach would adapt to the smoothness or structure of that CATE specifically, and not the individual regression functions, which by themselves are hard to estimate. So here's a plot of this sort of procedure. So the red line is the plug-in estimator. This is just taking the difference of those two estimated curves from the previous slide. And we can see it's doing a really poor job, right? It's way too wiggly, doesn't do a good job capturing the structure in the CATE. This IPW sort of approach where we inverse weight an outcome and do a regression, that's the blue line. So it's doing much better, right? This is all just using standard tuning parameter choices in R, not doing anything hand wavy here. And then the black lines are some doubly robust versions of this approach that I'm going to talk about in the first half of this talk. And so the basic story here is that all of this wiggly bias that we get from the plug-in estimator, which comes from the fact that we are bound to how well we're estimating the regression functions, goes away when we use these IPW and doubly robust approaches here. And the doubly robust approaches improve on variance quite a bit. And so this was just one sort of representative simulation, but this is the general story you see across hundreds of simulations. So for this data generating process, you see improvements in bias, which are just massive over the plugin because the regression functions are hard to estimate. And these sort of doubly robust estimators that I'll talk about in a bit can improve the variance as well by a huge amount. All right, so the main goal of this work is to study these kinds of procedures. In the first part of the talk, we're going to give some model-free guarantees that let us say something about how these things work in a very general setup. And then in the second part, we're going to try and pursue this question of how well we can possibly estimate a conditional effect. All right, so getting started with this first half, we're going to think about a two-stage doubly robust estimator, which I'll describe to you in just a second. I'm going to call it the DR learner. This is following this naming system that's sort of caught on from this Causal paper, where you call estimators letters and then learner. So a variant of this approach was actually proposed by Mark van der Laan in 2013 and also described further by Alex Ludka in 2016. But they didn't give any specific error bounds for the CATE. So that's sort of the extension that comes from this work. And then in some, what seems like independent work in later years, some people used kernel versions of this approach. So here are some citations there. But they use some pretty restrictive assumptions on the nuisance estimators here, which are the propensity score and the regression functions, or they didn't consider the case where the CATE has some extra structure or smoothness. So that's how we're adding to some sort of previous related work. Right. All right, so I'm going to just describe this approach first to you, and then I'll show you a picture of how this works. So we have one big sample of observations, and we're going to split it into 3 folds, and 2 of them are going to be used for training, and then the third is going to be used for a second stage regression. So in the training folds, we use one of the folds to estimate the propensity score, pi. We use another fold to estimate the regression functions under treatment and control. And then in that third fold, we take these training estimates, we construct a specific pseudo outcome here, which is just the uncentered influence function for the average treatment effect. If you've used a doubly robust estimator, this is just exactly what you average to estimate that sort of thing. And then instead of averaging it, we regress it on covariates in the second sample. the third sample actually. And so I'm going to use this notation here, E hat n, which is just going to denote some generic regression estimator. And it turns out we can be largely agnostic about this approach in general. And so here we've only used like n over 3 of the samples in this last stage regression. If you want to recover the full sample size efficiency, you can just swap samples here. Repeat this process using different folds for the training and second stage regression. And that doesn't add anything sort of interesting to the analysis. So I'm just going to think about the single sample split version, but all the results hold for the cross-fit version as well. All right, so here's a diagnostic for this approach. Just a schematic of what's going on. So we've got our big data set, X, A, and Y. I'm going to split it into 3 folds. For one fold, I'm going to estimate the propensity score. In another separate independent fold, I'm going to estimate the regression functions. I'm going to take these 2 things, mix them up, and estimate the pseudo outcome that I showed on the previous slide. And then in the third fold, I'm going to do just a generic regression of the pseudo outcome on X. So that's the procedure. It's very simple, straightforward. And this is what van der Laan proposed modulo the sort of slightly weird sample splitting where we estimate propensity scores and regression functions on 2 separate samples, but this isn't actually crucial for this approach. So, all right, so we're going to give an error bound for this procedure that works under very weak conditions, but we're going to need some stability of the second stage estimator. So we don't actually have to assume anything about the first stage. The second stage, we have to use this mild stability condition. So by stability, I mean that this regression in the second stage has to satisfy this property. So if we add a constant to our estimator, it behaves the same as if we add a constant to our outcome and then do the regression. So sort of adding a constant pre versus post regression is the same. It doesn't actually have to be exactly the same for this, the bound that I'm going to show to hold. It just has to be approximately equal. This is a very mild condition that you can show holds for lots of estimators. And then the second condition is that if I give you 2 random variables that have the same conditional expectation, then the mean squared error of this regression using either of these random variables has to be the same up to constants. So it has to scale the same within. This again should hold for sort of any reasonable estimator. Okay, so now we're ready to give an error bound for this procedure. So we need to assume that the propensity score estimates are bounded and the stability condition for the second stage regression. And now we're going to see how the error compares to an oracle that actually did a regression using the potential outcomes themselves, the y1 minus y0, or just random draws from these conditional distributions if you don't want to think about potential outcomes. So that oracle estimator has some risk, which you can, right here, I'm using mean squared error. You could use other things as well. Okay, and so the result is, as long as the propensity score estimates are bounded and we have a stable second stage regression estimator, then the mean squared error of our DR learner procedure looks like the oracle mean squared error up to this gap, which is like the product of mean squared errors for the nuisance stuff, the propensity score and the regression function. So this is sort of an analog of a usual kind of doubly robust style result, but for a conditional effect here, and that works for arbitrary second stage regression estimators. Right, so this is essentially model free. We don't need to assume anything about these estimators, but beyond this stability, it's a finite sample result. There's no asymptotics. And really what's buying you all of this stuff is the sample splitting. And so the really important part of this result is that we have this product of mean squared errors and the error bound, and that means we can get fast rates for the conditional effect, even when we're estimating the nuisance stuff at slower rates. This is similar to the phenomenon that you see for doubly robust estimation of average treatment effects. It's why we can live with end of the quarter rates in that setting and still attain root-in rates, for example, for estimating the average treatment effect. And so this, even though it's very general, it sort of applies to any estimator, it actually gives smaller risk bounds than what appeared in the previous work, either because they had a larger remainder error just from loose bounds, or they didn't use the smoothness of the CATE and so got a larger oracle risk. Okay, so yeah, this first result is sort of a model-free result. It requires this mild stability, and so we're just going to illustrate how this works in a few classic sort of non-parametric models where things are smooth or sparse. These are cases where local polynomial estimators or series estimators might work well in the smooth regime, or lasso might work well in the sparse regime. And so these are just some illustrations, but you could, if you know anything about the mean squared error of any of these, any given procedure, you could just immediately get out bounds from this result. Okay, so for thinking about smoothness, this will play a large role in the second half of the talk as well. We're going to refer to S-smooth functions. These are functions in the Holder class, H with index S. Intuitively, these are functions that are just close to their S-1 order Taylor approximations. And so more formally, they have S-1 continuous derivatives are all bounded, and then the S-1 order partial derivatives are all Lipschitz. This is classic function space in non-parametrics. And you should think of S as like the number of derivatives basically that you have. Okay, so now we're going to apply this error bound that we have for this DR learner approach in the smoothness setup. So we're going to think about the case where the propensity score is alpha smooth, so that we can estimate it with mean squared error n to the minus 2 alpha over 2 alpha plus d. The regression function is beta smooth, so we can estimate that at n to the minus 2 beta over 2 beta plus d. And then we're going to think about the case where the CATE has its own smoothness, gamma. And so the sort of setting you should think about here is where the CATE might be smoother than the regression functions. So it can't be less smooth. So the difference has to be at least as smooth as the individual regressions, but it could possibly be much smoother. And then we also have this propensity score smoothness floating around. So if that second stage regression method is minimax optimal for gamma smooth functions, then we get the following result. We get a mean squared error from this approach, which looks like this first term here. It's n to the minus 2 gamma over 2 gamma plus d. That's the oracle rate. That's the rate that we would get if we actually observed the potential outcomes and could just do a regression of them on X. And then the second term here is the product of the mean squared errors for the two nuisance functions, the regression and the propensity score. And so this implies sufficient conditions on this DR learner being oracle efficient, so attaining the rate of this oracle estimator. And this is what the sufficient conditions look like. If you think about the case where the propensity score and the regression are equally smooth, things simplify a little bit, and we get that the nuisance smoothness has to be greater than d over 2 divided by some inflation factor that's greater than 1. And that inflation factor is sort of interesting, especially compared to the average treatment effect. So I'll talk about that in just a bit. But before we do that, I just want to give you a picture of what these rates look like. If you're not used to thinking about them, it can be weird to see all these numbers floating around. So here's just a picture illustrating. So this is a specific setup where we have 20-dimensional X. The CATE is relatively smooth. It has smoothness equal to twice the dimension. And then we're seeing how in this case, the root mean squared error changes as a function of the smoothness, S. Okay, so this first dotted line is the minimax lower bound, which Jamie derived for the ATE a number of years ago. And this is also sort of the classic minimax rate for functional estimation. This is n to the minus 4s over 4s plus d. So this won't be attainable for the conditional effect. This is a harder statistical problem, but I'm putting this here just for reference so we can see how things compare. Right, so here's the oracle rate. This is the rate that we would get if we actually did a regression of the potential outcomes on X. This is just depending on the smoothness of the CATE itself. And so this is sort of one benchmark, but we're not always going to be able to attain this benchmark. Here's the plugin estimator bound. So this is just the bound that you get from estimating the regression functions themselves individually. And so for this plugin estimator to have mean squared error that looks like the oracle, we need the regression functions to be as smooth as the CATE. They need to have equal smoothness. And so otherwise, this sort of plugin approach, unless it's sort of specially tuned, in general wouldn't hit this oracle rate. And then here's the bound that we get from the DR learner from the previous result. And you can see that it actually attains this oracle rate sort of much more quickly as a function of smoothness than the plugin. In this case, you need something like average smoothness of 7. Right, so that's just a picture of these rates. We'll come back to this as we add more rates in the picture. Okay, so overall, this shows that using this approach can allow you to adapt to the smoothness of the CATE. Even when you have less smooth propensity scores or regression functions, you can get nice sufficient conditions for achieving this oracle rate. And it's sort of interesting to think about how they compare to the corresponding sufficient conditions for the average treatment effect instead of the conditional effect. So for the average effect, the condition that you need for a standard doubly robust estimator is that the geometric mean of the smoothness, so the square root of alpha times beta, is greater than d over 2. So there's some interesting alignment here. As the CATE becomes infinitely smooth, you start to recover this ATE sufficient condition, which you might expect, right? As the CATE is infinitely smooth, it sort of comes back to this problem of estimating the average treatment effect. They should have sort of roughly the same statistical difficulty. But as the CATE smoothness goes down, the bar is sort of lowered for how well we need to estimate these nuisance functions in order to achieve the oracle rate. In the extreme, when the CATE has 0 smoothness, the plugin estimator will do well. So the term that you subtract from the sufficient condition, this d squared over 4, is sort of like representing this lowered bar that we need for optimal estimation in these problems. There's kind of an interesting trade-off here where it's a harder statistical problem than average treatment effect estimation. You get slower rates necessarily because it's a nonparametric regression type problem. But the upside is that you can achieve oracle rates under relatively weaker conditions. And so this kind of thing has come up, it came up in the dose response estimation problem as well, which is sort of similar in spirit in some ways. But I don't know that it's been mentioned in the CATE problem specifically. Okay, so that's the smoothness model. So now we're going to think about a sparse model, a sparse high dimensional model. Right, so we're going to say that the propensity score is alpha sparse. Again, this is just an illustration of this previous sort of model-free result, showing that it works in a variety of different contexts. All right, so the propensity score is alpha sparse. So that means ideally under sort of maximal conditions, we can estimate it at a rate alpha log d over n. Similarly, the regression functions are beta sparse. They have their own sparsity, so we can estimate them at beta log d over n. So if the CATE is gamma sparse, and that second stage estimator yields the right mean squared error, gamma log d over n, then we get a sparsity, we get a rate that looks like the oracle sort of sparse rate, gamma log d over n, plus again, this product of mean squared errors. And so you can figure out from this what the sufficient conditions are for oracle efficiency. In this case, it turns out to be that the product of the sparsities has to scale faster than gamma n over log d. So again, it's sort of interesting to compare this to the ATE case, the standard doubly robust estimator. So the sufficient conditions for root inconsistent estimation in that setup, which is sort of like the oracle, were given in this 2015 paper by Max Farrell, and they're basically of the form the product of the sparsities has to be less than n over log squared d. And so again, we see the same phenomenon that the sufficient condition in this case for this DR learner approach is less stringent. So just a simple example to think about, specific numbers with these rates. So let's say that gamma is scaling like root n over log d. That means that the oracle rate is n to a quarter. So the oracle rate here would be achieved if the product of the sparsities, just using that sufficient condition that we get from the theorem, is less than in root n over log squared d. So we get an extra root n factor. That means we can live with up to n to the quarter less sparsity on each of the nuisance functions and still achieve the oracle rate. So just another example of how we have, it's a harder statistical problem, but we have a lower benchmark for attaining oracle rates here. Right, so I'm going to go over some simulations here. So yeah, we're going to think about just some finite sample properties in this high dimensional setup. So here's a case where we have high dimensional linear models, D covariates X. Everything's linear with some sparsity, beta in the regression function, gamma in the CATE, and then the propensity score follows a logistic model here with alpha sparsity. So we're going to use that condition on the sparsity, on the nuisance sparsity, that tells us the oracle should be achievable based on our results. So this means the alpha and beta sparsity scale like root gamma n over log d. And then we're just going to pick some CATE sparsity and see what happens. We're going to set gamma to be 20. So 20 of these coefficients in the CATE model are non-zero. All right, so I just simulated some data from this setup, and then I used lasso everywhere to do all the model fitting. So I estimated all these nuisance functions with lasso, cross-validation to lasso, and then I did the second stage regression for the DR learner also using lasso. And then I compared 4 different estimators. So we looked at the plugin. It's also called the T-learner. So it just takes the difference of mu1 hat minus mu0 hat. So I just estimate both these regressions and take a difference. The X-learner, which is similar to a plugin, it does something a little bit different. So it estimates mu0, for example, and then goes to the treated sample and takes the difference y minus mu0 hat and regresses that on X. To get an estimate of the effect, and then does the reverse in the untreated sample and combines them. This comes from that Causal paper. And then we use the approach that I gave earlier, this DR learner thing, where we estimate the propensity score, the regression function using lasso, and then go to this third sample and do the second stage regression of that influence function pseudo outcome on the X's. And then I also give an oracle that has access to the true nuisance function. So it's using this DR learner procedure, but has the true nuisance stuff. So here's what we see. So this is showing the mean squared error for these 4 approaches at different numbers of covariates. So we've got D equals 100, 500, and 1,000. And the story is basically the same across all of them. So we see a massive improvement in mean squared error using this approach. Because it's not bound just to the sparsity of the regression functions like the plugin and the X-learner is. And then we also see that the DR learner is matching the oracle essentially, even in pretty challenging setups where we have as many covariates as we do samples. So we're still getting quite close to the oracle, and this is what we'd expect is this result, as a finite sample result. Here we're starting to lose something in terms of constants, but otherwise we're doing well. Yeah, so you can really see some massive improvements here in practice doing this sort of thing. So just quickly, I want to mention, in the interest of time, that underlying this bound, there's a general oracle inequality that was actually used to derive this. That applies in general to regression problems where you have an unknown outcome that you need to estimate. And this comes up in a lot of problems actually, estimating V-specific conditional effects. So, we're thinking about the case where we're estimating a conditional effect given all the covariates, but you could estimate an effect just given a subset of them. Regression, when you have missing outcomes, this is sort of equivalent to the causal inference problem in some sense. estimating the dose response curve for a continuous treatment or heterogeneous effects of continuous treatments. These also can be framed as this sort of nonparametric regression problem when you have an unknown outcome. Conditional IV effects, partially linear IV. So lots of problems have the same structure. And yeah, I think I'll just go quickly through this, but there's a corresponding oracle inequality that looks like what we saw with the DR learner, but that applies in a general two-stage nonparametric regression procedure when you have nuisance functions. And an important feature of this, again, it has all the same properties as that previous bound. It's model-free apart from the stability condition, uses sample splitting in the same way. And it gives you a gap here, which can be really informative in practice. It's what gave us that double robustness before. I haven't seen something like this in the literature before. So I think that can be useful in practice. Okay, so I think maybe I'll stop here for questions if there are any.
Yeah, thanks, Ed. So in the interest of time, we'll just ask one question. So let me unmute Judith. So 1 second. All right, Judith, you should be unmuted.
Edward, I was wondering, what are the kind of estimators that make your condition 2 on slide 10 hold?
Condition 2. So yeah, that's the yeah. If you give me 2 random variables with the same conditional expectation, I get roughly the same mean squared errors. Yeah, I think that should hold for essentially any sort of standard nonparametric estimator. If you look at typical error bounds, you know, they don't depend at all on, you know, variances. So as long as the variance is not 0 or infinity, I think this will typically hold.
Well, that was one of the things that I wondered, if the distribution of the errors is different, do things change? I could imagine they could.
It should only affect constants unless the variance is like blowing up or going to 0, not rates. Yeah, that's a good question.
Thanks, Judith. Okay, so we won't have time for more questions, unfortunately, but yeah, you have another 10-ish minutes, Ed.
Great. Okay. All right. So yeah, that sort of wraps up this first part where we give this, you know, model-free result, sort of practically useful. We don't need any undersmoothing or anything. Works with a wide variety of estimators. Now we're going to try and think about the best possible performance we could get at estimating the conditional effect. And so to do this, we're going to analyze a sort of more specialized estimator and see, you know, just try and optimize performance, see what sort of rates we can get. Right, and this comes from, you know, we have this error bound from the previous result, but we don't know what happens if this product of mean squared errors is not small enough, right? So if that's not small enough, we know that this bound is saying we don't know whether the oracle rate is achievable or being attained, and so this is what we're going to try and get at here. So I'm going to analyze sort of interesting estimator. So it's a double sample split local polynomial adaptation of the R learner or double residual regressions. The R learner is a nice non-parametric extension of this double regression method of Robinson from the 80s. Some series version of this was studied by Jamie in the experimental setup. Yeah, it turns out we can get some nice weak sufficient conditions for oracle rates here, and we can also explore what happens outside of this oracle regime. So let me just move forward. So this is a schematic for the approach. So again, we split our data into 3 folds. We're going to do something a little bit different here, though. So in the first fold, we still estimate the propensity score, pi hat, but now we use the second fold slightly differently. We use it to estimate the propensity score again. So we get 2 propensity score estimates, and we get an estimate of that marginal regression of y on x. We take both of these propensity scores. So just big picture, this procedure looks like a kernel weighted least squares regression. of residuals, outcome residuals on a basis expansion times treatment residuals. So that's the idea. So here we create the kernel weights using the propensity scores. Then we create these residuals, treatment residuals and outcome residuals. And now we're done with all the training. Now we move to the third sample and we do a kernel weighted least squares of the outcome residual on a basis, typical local polynomial basis expansion. So all polynomial orders up to the smoothness of the CATE times this treatment residual. And then the weights are these kernel weights multiplied by some factor that is essentially estimating 1. So that's the procedure. It's a little more complicated, a little more convoluted. Again, the point here is less about using this thing in practice. I think it likely will work in practice well, at least under some conditions. You have to figure out the smoothing and things, but the point here is to try and explore the fastest rates that we could possibly get under weak conditions. All right, so we're going to use some conditions on the nuisance estimators. We're going to assume that they're linear smoothers, that they have variance that scales like k over n, and that their bias is like typical bias that you'd see in a Holder smooth model. So for the propensity score, k to the minus alpha over d. For the regression, k to the minus beta over d. So these are our standard conditions in the nonparametric setup. Lots of estimators, it turns out, are linear smoothers. The variance condition here holds, for example, for local polynomials and series estimators, standard series estimators. The bias as well, this holds under Holder conditions. These are all sort of standard setups. All right, so let's think about this first error bound for this procedure. All right, so I'm going to assume everything's bounded just to make my life easier. The propensity score is bounded as well. Got an eigenvalue condition here, which I'm not going to go into detail about, but it should hold for standard choices of tuning parameters. And then I'm going to use this nuisance condition that we're using linear smoothers with variance and bias bounds that you get under Holder kind of assumptions. So then if the CATE is gamma smooth, you get a rate that looks like this. So we're going to talk about this in detail. It has 5 terms, 3 are biased, 2 are variance. And the objects appearing in this rate are the smoothness of the nuisance stuff and the smoothness of the CATE itself. And then the 2 tuning parameters. So the 2 tuning parameters are the second stage kernel weighted regression bandwidth, and then the first stage nuisance estimation, which is the K tuning parameter. Okay, so let's think about the bias. The bias has 3 terms. The first term, H gamma, is just the oracle bias. It's the bias you'd get even if you did a nonparametric regression of the actual potential outcomes on X. We're never going to be able to get away from that. The other 2 terms are the ones that come from the nuisance estimation, so they involve K. The first one is the product of the biases for estimating the propensity score and the regression function. That's k to the minus 2s over d. The second one is the squared bias for estimating the propensity score. And this is sort of what you should expect actually to get here. So this method, which I don't think I said the name of, I'm calling it the LP-R learner. So it's an R learner that's a local polynomial extension. So this is just it's a kernel weighted least squares. It has some weird sample splitting and stuff, but essentially it's a least squares estimator. And so it has an X transpose X inverse type term that involves the propensity score estimates. That's where the squared propensity bias is coming from. And it has an X transpose Y type term, which involves the propensity score and the regression estimates. And that's where the product bias is coming from. So this is sort of what we should expect to get. So those are the 3 bias terms. The variance terms, one again is the oracle term that we're not going to be able to escape. And the other is a nuisance term. And it looks like the product of the nuisance standard deviations times the oracle standard deviation. So it turns out that this variance contribution from the nuisance estimation is typically going to be lower order in standard settings because we need to take that tuning parameter in the nuisance setup k to be less than n. And so that immediately sort of tells you that the way to optimize this procedure is to undersmooth as much as possible to drive down the bias of the nuisance estimation, because up to order n, it doesn't actually affect the variance. So this next result just says what happens if you do this. So you get a rate that looks like the oracle plus n to the minus 2s over d. This n to the minus 2s over d rate comes up in some other problems, conditional variance estimation. It's actually the minimax rate for some functional estimation problems like the average treatment effect in a fixed design. And you can see from this what a sufficient condition is for achieving the oracle rate. Looks like S greater than D over 4 divided by some inflation factor.
And
so let's think about,
can you in 2 or 3 minutes?
Yes, sounds good. So let's think about what this is saying. So yeah, this is much weaker than the condition we get from the DR learner. The trade-off is we have to use this sort of specialized estimator. So it's a lower bar. There's sort of an interesting interaction with the CATE smoothness. So when the CATE is more smooth, this starts to align with the actually necessary and sufficient condition for root n rates for ATE estimation. That's S is greater than D over 4. As the smoothness goes down, you lower the bar that you need to attain this oracle rate. And I think this is probably minimax optimal, but I haven't proved it. And yeah, the rate you get here is slower than the usual minimax rate. So let's look at a picture. Got the minimax rate, the oracle rate, just like before. Here's the plug-in rate, it's slow, the faster DR learner rate. And then here's the rate that we're getting now with this specialized estimator. So it's hitting the oracle rate, you know, at almost half the smoothness that you need for the DR learner. So the last thing I just want to mention here is that you can actually, it's somewhat surprising. So the CATE doesn't depend at all on the covariate density. It's conditional on the covariate density, on the covariates. But if you know the covariate density, you can actually exploit this to get faster rates. And maybe I'll just refer to the paper in the interest of time. But the rate you get, if you know the covariate density, that means you can drive the bias down even further. And you get this interesting rate, it looks like n to the minus 3s over 2s plus d times something. And so an open question is whether this is a minimax rate. I think it is, but I don't know for sure. This gives you the same elbow at the oracle rate, so it's not improving the place at which you hit the oracle rate. But yeah, so here's a picture of that rate that I think is probably minimax. And that's it. So just to wrap up here, we've got you know, this procedure, the DR learner, a model-free error bound, got a general oracle inequality for this thing that works you know, in any sort of two-stage regression procedure, and then an estimator that sheds some light on what kind of rates we could expect as a benchmark in these problems, so we can know you know, what the best possible performance is. Again, overall, the goals are to give some flexible tools. The first half more practical, the second half more just understanding how well we could possibly do. So I've got some discussion points here. I think I'll skip that. You can look at the paper. Paper should be on archive tomorrow. I want to thank Siva Balakrishnan for really useful discussions. And yeah, thanks everyone for attending.
Fantastic. Thank you, Ed, for this great talk. That's what was very interesting. So we're now going to switch to the discussion. We have Jamie Robbins say a few words, and then afterwards, if there's you can respond, Ed, and then if we have some time left, we might ask some more questions. So I'm now switching over to Jamie. Jamie, you should now be unmuted.
Okay, and do you see my screen?
We don't see the screen yet. Can you try sharing again? Yeah, now we see it.
Okay. So I'm going to discuss Edward's really beautiful talk. I'll explain what I'm going to do here. So I read the paper. I didn't see the slides when I made this, but he covered most things. Paper was filled with interesting results, both practical and theoretical. The DL learner estimator was in particular practically very useful. It was easy and natural to compute, but as he said, it was not minimax optimal, and the oracle rate is not achievable. here I have a question for Edward, because it's the one thing that doesn't fit into my way I see things, why he would need to estimate pi and the mu's from different samples in his net estimator. From different, why couldn't they be estimated from the same split sample from the main sample? Okay, so one goal of this paper was to construct an estimator. His LP learning would be minimax optimal under Holder smoothness. And I'm going to discuss this point as I was interested to see what the higher order influence approach would give for estimating the same function. My goal is to use already available results for higher order influence functions to reproduce and sometimes improve on Edwards' result with just back of the envelope calculations. With higher order influence estimate, one does not have to be as clever as Edward to produce an unusual estimator like his local polynomial R learner, which he has two propensity scores, which he estimates from different samples, which is an even more creative version of my double sample splitting estimators, which I'll get back to, that I introduced Whitney Newey. The disadvantage of I just told you they can do better, but their disadvantage is that they may require one to compute very high order U statistics, which causes both statistical and computational problems. So it's best to think of the higher order influence function estimators as often being a gold standard estimator, because they usually are, if something could be minimax, they may be whose properties you wish to equal simpler estimators that don't require high order U statistics. So I want to point out that what I'm doing here is Monday morning quarterbacking or reverse engineering. I mean, Edward had these beautiful results that I didn't know and didn't have immediately any intuition for, and I wanted to see how I could get intuition using the machinery I knew. So the main conclusion I get is in his theorem 3, that's where he's using the minimax estimator without f of x known. He imposes, in order to get the minimax rate of n to the minus 2s, where s is the average smoothness of the propensity score and the outcome regressions, he has to assume that the smoothness alpha pi exceeds the smoothness beta of the outcome regressions. And I'm not putting d here. Whenever you see a beta, I really mean beta over d. So this, where d is fixed dimensions, but so you could think of it either as one dimension or beta means beta over d. So the higher order influence function gets this n to the minus 2s always without needing the smoothness of pi to exceed that of beta. And in theorem 4 with f of x known, I also don't need that alpha greater than or equal to beta, but but there are more subtleties. I probably don't have enough time, so let's try to ignore that. Go on. Okay. 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 So how did I do back of an envelope with higher order to get his results a little better sometimes with higher order influence functions? Well, I was interested in the conditional treatment effect. I wrote it as a Fourier series where phi of L were orthonormal bases with respect to f of x. And if I don't know f of x, I can do various other things. So that's not critical for what I'm doing here, but think of it as an orthonormal basis with respect to f of x. And then I took the projection on the first case. I just threw away all but the first case star basis functions. So what is K of L? It's the expected value of the function with the basis function, which we know is the expected value of y times a minus pi over pi times 1 minus pi times basis function. But notice, you'll see clearer what's going on here. I can write this algebraically is the expected value of a over y pi times phi L minus the expected value of 1 minus A over 1 minus pi Y times phi L. So if the phi L wasn't here, this is just, you know, the treatment effect if everyone was treated, and this is the treatment effect if everyone's untreated. But here times phi of L, and so that makes sense because I'm taking the difference between the two. I'm estimating the treatment effect at level X. But notice, even though I'm doing it at level X, because that's what this is about, the K of L, the things I'm going to have to estimate to do this are in fact normal functionals. They're just like the mean of AY over pi, except there's a fixed function of X. So I'm actually just doing ordinary influence function-based estimation of a parameter with a finite semi-parametric variance bound, the K of L's. But later I'm going to have to put K star of them, that's kappa, not K, K star of them together. So I've reduced the problem into two parts, put K star together of ordinary kind of things we estimate all the time. So the things we estimate all the time, let me just go down. The things we estimate all the time, it's IPW stuff, we know everything about higher order influence function estimators of that. Okay, because it's just the ATE, but we multiply by a function of X, one for each alpha L. So we know that the bias of a higher order influence function estimator of alpha L is going to be K to the minus 4S, with S the average of the smoothness of the propensity score and the outcome regression. And its variance is K over N squared, plus a 1 over N term. The K is less than N squared. I left out the usual term. And that's, those are the bias provided when K is greater than N, you have a certain condition. That's the part I'm forgetting, so don't worry about that. Okay, so now we have to do K star of these. I'm estimating K star guys, so that's going to make the variance, because my final estimator is going to be a sample. I'm going to put, you know, the Fourier series up to K star, put my K hat, my higher order influence function estimator of kappa hat. And so the variance is going to be K over N squared times K star, because it's like estimating K, you know, betas in regression. It goes up. And the bias, I said, for the higher order influence function estimator of K is K to the minus 4S, but this should be K star. But I also get a bias for truncation because which should be K star to the minus 2 gamma, because remember, gamma is the smoothness of the treatment effect function I'm trying to estimate, and I cut it off at K star, so I have a truncation bias of K minus.
Jamie?
K star. Yeah.
Wrap up in a minute or so. We're running out.
Okay. So the optimal higher order influence function will equate the variance K over K star with the two sources of bias. And if you do that, that'll just give Edwards results, except you don't need the, generally you don't need the alpha greater than or equal to beta. And well, my last minute is the key thing that Edward did to be able to, so the way I look at him is he really used first order influence function estimators. But by doing this double sample splitting, Nie and I proved that if you have a functional that's whose influence function looks like the product of two linear residuals, then you can do as good as higher order influence functions by just doing first order influence functions if you estimate these guys from different samples, this guy and this guy. But the problem is the functional, the average treatment effect and the functional that Edward was estimating aren't of that form because they have an a minus pi, but then they have a pi in the denominator. And it's that pi in denominator that you can't use that method. So what I think essentially what Edward did is he expanded this around pi hat to get a term that looks like this with a real pi there. So now this is of the form two linear conditional expectations. So that's where he got the end of the minus 2s because that's as good as a higher order influence function. Unfortunately, he paid for it with a term that if you do the expansion, looks like a minus pi hat squared times some random variable plus something small. So he has to estimate, so that term gives n to the minus 2 alpha, the reason he needed alpha greater than s. So this doesn't dominate the bias. And the reason, and he has to estimate two versions of pi, one from one sample and one from the other, because it's only when you do double sample splitting, even if it's the same parameter, that you can get a first order estimator to be as good as a higher order influence function estimator and thus minimax. All right, I'm done. Anyway, it was a great talk, and this is my way of understanding it in my way, but it wasn't any ideas I had before I saw his.
Great. Thank you, Jamie.
Okay.
Do you want to say a few words?
No, yeah, I agree with everything Jamie said. Yeah, I appreciate the insight.
All right, great. I think we're running out of time, so unfortunately we will not have time for any more questions. 1 second, I gotta share my screen. So first, let's thank you very much, Jamie, and thank you very much, Edward, for a fantastic presentation and for a great discussion. It was very interesting. I learned a lot. Now, next week, we have Eric Chetkin from the University of Pennsylvania. We're very much looking forward to that also. Thank you all for joining, and hope to see you all next time. Thank you.